Okay, today we're looking at 11.3, the last new topic of the season, binomial theorem. We're going to first of all look at Pascal's triangle. You'll notice on Pascal's triangle, there's a first row of 1, a second row of 1, 1, third row of 1, 2, 1, fourth row of 1, 3, 3, 1, and the fifth row of 1, 4, 6, 4, 1. Now, if we had time to examine this, and I'm going to ask you in a different example on a different day to look at coming up with many different patterns if you continue this down to about 20 different triangles. But right now, if you made the next row, notice that you can find it by adding the two previous numbers above it. For instance, 5 is 1 plus 4, 10 is 4 plus 6, the next 10 is 6 plus 4, the next one is 4 plus 1, and the last is just a 1. If you expand the power of a binomial expression, such as x plus y to the fourth, you're going to get a series of terms. It's going to work out to be 1 times x to the fourth plus 4 times x cubed y plus 6x squared y squared plus 4xy cubed plus 1 y to the fourth. Now, you'll notice many patterns in x plus y to the fourth. One of them I hope you'll notice is all the coefficients. 1, 4, 6, 4, 1. All those numerical coefficients happen to match up to be the fifth row of Pascal's triangle. 1, 4, 6, 4, 1. Also, notice that x plus y to the fourth means that all of the exponents of all of the terms have to add up to 4. X to the fourth, y to the 0 for the first term, x to the third, y to the 1 for the second term, all the way across. And the coefficients of the binomial expansion can be determined from Pascal's triangle. And you'll notice for x plus y to the n, there's going to be n plus 1 terms, and you can find the coefficients in the n plus 1th row. Here's another pattern you might have had time to discover on Pascal's triangle. But our numbers in the triangle also work as combinations. Any number is C in the first row, 0 choose 0 is 1. The next row, 1 choose 0, 1 choose 1. The next row, 2 choose 0, 2 choose 1, and 2 choose 2. All the way down to the number I have circled, 5 choose 2, which is the example shown. And that's going to be equal to 10. Because 5 choose 2 gives me 5 factorial over 5 minus 2 factorial times 2 factorial. Here in example 1, we're going to first of all expand p plus q to the power of 6. So we're going to say if we used combinations, the first coefficient is going to be 6 choose 0. So we're going to say p plus q to the 6th. The coefficient is 6 choose 0 for the first term. Then we're going to have p to the power of 6, q to the power of 0 for the coefficients. For the second term, we're going to have 6 choose 1. Next is going to be p to the power of 5 and q to the power of 1. Then we're going to move to 6 choose 2 for the third coefficient, p to the fourth q squared. 6 choose 3, p to the third q to the third. 6 choose 4, p squared q to the fourth. 6 choose 5, p to the 1 q to the fifth. And lastly, 6 choose 6, p to the 0, q to the sixth. Now, and if we use the patterns in Pascal's triangle, we can figure out what all those 6 choose 2s are and 6 choose 5s are. And those are going to be the patterns of 1 from the 7th row. And it's going to be 1, 6, 15, 20, 15, 6, and 1. Notice because it's p plus q to the power of 6, there's 1, 2, 3, 4, 5, 6, 7. n plus 1, again, number of terms. So both ways result in p plus q to the 6th is going to be 6 choose 0, which is 1 p to the 6th times q to the 0, which simply is p to the 6th, plus The next one is 6, and that's going to be p to the 5th q to the 1, plus the next one is going to be 15 p to the 4th q squared, 20 p cubed q cubed, 15 p squared q to the 4th, plus 6 p times q to the 5th, plus 1 q to the 6th. Some patterns you may have discovered are that there's 6 plus 1, or 7 terms in the expansion of p plus q to the 6th. The powers of p are going to decrease from 6 to 0, and at the same time the powers of q are going to increase from 0 to 6. Each term is of degree 6. That's the sum of our exponents. And the coefficients are going to be symmetrical, at least in this example. They're going to begin and they're going to end, in this case, with 1. Okay, in blue, you can use the binomial theorem to expand any power of a binomial expression. If you have x plus y to some power of n, the coefficient for the first term is n choose 0. The coefficient for the second term is n choose 1. The coefficient for the third term is n choose 2, n choose 3, n choose 4, all the way down to the last term, which is n choose n, for n number of terms. Now the variables. X is the first variable. For the first term, it's going to be x to the power of n. For the second term, it's x to the power of n minus 1. Third term is n to the minus x to the n minus 2, all the way down to the last term, where you have x to the power of 0. It keeps decreasing by 1. At the same time, the y value is going to start at 0 and increase all the way until it is at n. In this chapter, all binomial expansions will be written in descending order of the exponent of the first term in the binomial. The following are some important observations about the expansion of x plus y to the n, where x and y represent the terms of a binomial and n can be any natural number. The expansion is going to contain n plus 1 terms, always one more than the exponent. The number of objects k selected in the combination n choose k can be taken to match the number of factors of the second variable selected. That is, it's the same as the exponent on the second variable. And that means that the general term, t, the term of k plus 1, has the form of n choose k and x to the power of n minus k, and y is going to be at the power of k. Lastly, the sum of the exponents in any term is the expansion of n. So if it's x plus y to the 4th, the sum of the exponents will always be 4. Example 2, using the binomial theorem. We can use the binomial theorem to expand 2a minus 3b to the power of 4. Here we go. We're going to say 2a minus 3b to the power of 4 is going to start out with the coefficient 4 choose 0. Then it's going to be 2a to the power of 4, and then it's going to be negative 3b to the power of 0. First term. Second term, plus 4 choose 1. That's going to be 2a to the power of 3 and negative 3b to the power of 1. Notice that the a's are going to go down by 1 power each time, and the b's are going to keep increasing by 1 power. So then 4 choose 2, 2a squared, negative 3b, 2, plus 4 choose 3, 2a to the power 1, negative 3b cubed, plus lastly 4 choose 4, 2a to the power 0, and negative 3b to the 4th. Now for the next part, remember that you're going to be picking numbers from the 5th row of Pascal's triangle. The coefficient is going to be 1. 2a to the 4th, well 2 to the 4th is 16. A to the 4th is a to the 4th times negative 3b to the power of 0, which is 1, plus. Second term now. 4 choose 1 is 4. 2a cubed will be 8a cubed. And negative 3b to the power of 1 is negative 3b. Plus 4 choose 2 is 6. 2a to the power of 2 is 4a squared. Negative 3b to the power of 2 would be 9b squared. Plus 4 choose 3, that would also be 4. And then 2a to the power of 1 and negative 3b to the power of 3, which is negative 27b cubed. Lastly, 4 to the power of 4 choose 4, is 1. 2a to the power of 0 is 1. And negative 3b to the power of 4 is 81b to the fourth. Lastly, let's simplify all these terms. 1 times 1 times 16 is 16a to the fourth, minus 96a cubed b for the second term, plus 216a squared b squared, the third, minus 216, that's what you get when you go 4 times 2 times negative 27, and lastly, 1 times 1 is 81b to the fourth. That's your final answer. B. Let's find the third term of the expansion 4b minus 5. Well, remember the first term is going to have a coefficient of 6 choose 0. The second term will have the coefficient of 6 choose 1. So the third term is going to have a coefficient of 6 choose 2, which is 6 factorial over 4 factorial times 2 factorial, which is 15. There's our coefficient, 15. Now, we've got to figure out the variables that go on the end of 15, our coefficient. And since the first term is going to have 4b to the power of 6, the second term is going to be 4b to the power of 5. The third term has to be 4b to the power of 4. Third term is 4b to the power of 4. So there you have it. 15 times 4b to the power of 4 times negative 5 squared, which is 25. Multiply those out, and you're going to get 96,000b to the fourth. Lastly, C. Let's look at first few terms of a squared minus 1 over a to the power of 5 and see what pattern is developing. Then we'll be able to tell which term will contain just a, or a to the power of 1. So if you expand this a little bit, we don't really need to know what the numbers are, the coefficients are. We just need to know what term it is. The first term is a to the squared to the fifth, negative 1 over a to the power of 0. If I simplified that, that would be a to the power of 10. So the first term is going to be to the power of 10. The second term, a to the squared to the fourth, is 8. And negative 1 over a, that's a to the negative 1, that would be a to the power of 7. So the first one was a to the 10, second one was a to the 7th. The third one, 5 choose 2, a squared cubed is a to the 6th. Negative 1 over a squared is a to the power of negative 2. That would be 4 to the power of 4. So we're going to the power of 10 to the power of 7 to the power of 4. There's 10, there's 7, there's 4. Therefore, the pattern shows a decrease by 3 each term. So if we went 10, 7, 4, the next term should be a to the power of 1. So we can say it'll be the fourth term that it's going to be. There we go. That's it for this lesson. Congratulations, you've done the year.